What if you could unshatter a glass, not just rewind a film of the event, but to actually reach into the fabric of space-time and command the scattered shards suspended in their chaotic flight to reverse their journey? Imagine those fragments pulling themselves from the floor, defying gravity, retracing their explosive paths through the air to seamlessly reassemble, culminating in the perfect, pristine vessel resting once more in your hand. The sound of the crash would play in reverse, a sharp crack imploding into a soft thud, the echo contracting into silence. The cause, the slip of your fingers, the fall would be erased from history, undone by an effect that now lies in its future. It sounds like magic, a violation of everything we know. It feels impossible because it is. This is the first and most fundamental law we ever learn long before we have the words for it. It is the bedrock of our sanity, the ruthless logic that underpins our every action, our every thought, our every memory. Cause, then, effect, always in that order, one direction, no exceptions. This unyielding progression is what we call the arrow of time. It is the silent, invisible current of the cosmos, a river that flows from a fixed past toward an open future, carrying all of existence along with it. This forward momentum is the scaffolding upon which our entire universe is built. It dictates that stars are born from collapsing nebulae, not the other way around. It ensures that life evolves from simple organisms to complex beings, a story written in one direction across billions of years. It is the principle that allows you to remember your childhood but not your death. Your memories are footprints left in the sands of a past that is gone forever, while the future remains an undiscovered country, a realm of pure potential. The chain of causality is absolute. An event happens, and its consequences ripple outward, spreading through space-time like shockwaves from an explosion. Those ripples never ever converge back to a point before the blast. To suggest otherwise is to speak a language of paradox and chaos, to propose a reality where the script of existence can be edited from its final page. Our entire civilization, our science, our philosophy is a testament to this inviolable sequence. We build bridges because we know the principles of physics will hold that the load will cause a predictable stress. We plant seeds with the certainty that sunlight and water will cause them to grow. We make choices believing that our decisions today will shape the outcomes of tomorrow, not yesterday. This is the essence of free will, the very notion of agency, that we are the authors of what is to come, not merely the readers of a story already written. The past is concrete, immutable, a vast and silent museum of moments that can be studied and learned from but never changed. The future is a fog, a landscape of possibilities that we navigate with every step we take. This one-way street of time is so deeply embedded in our perception of reality that to even question it feels like a form of madness. It is the ultimate truth, the final and non-negotiable rule of the game. But what if it isn't? What if this bedrock principle, this seemingly unbreakable law that governs every moment of our lives, is nothing more than a local ordinance, a powerful and convincing illusion that holds true in our large-scale, classical world, but dissolves into something far stranger, far more mysterious in the universe's hidden basement? What if, when we descend to the smallest possible scales, into the bizarre and ghostly realm of the quantum, we discover that the river of time is not a river at all? What if it's a vast, shimmering ocean where currents can flow in all directions at once, and where echoes from a distant shore can travel backward to meet the waves that have not yet formed? For over a century we have been haunted by the behavior of this subatomic world. A world that operates on a logic so alien, it forces us to abandon our most cherished intuitions. Down there in the seething foam of quantum reality, particles can exist in multiple places at once in a ghostly state of pure potential called superposition. They can be linked across impossible distances by a mysterious connection Einstein famously called spooky action at a distance, a phenomenon we now call entanglement. It's a place where the simple act of observation, of looking at a particle, can fundamentally change its reality, forcing it to choose a state out of a cloud of probabilities. This is a universe that seems to respond to our questions, a reality that seems to be in a constant state of negotiation. And it is here, in this realm of sublime weirdness, that some of the most brilliant and audacious minds in physics have dared to propose the ultimate heresy. They have asked a question so profound it threatens to shatter our understanding of everything. What if at this fundamental level, an effect can precede its cause? This is the explosive, mind-bending concept of retrocausality. It is the radical proposition that the future can influence the past, not in the grand paradoxical way of time machines and changing history, but in a subtle quantum whisper. An idea that a measurement made on a particle times now times might be able to reach back in time and alter the properties of that same particle or its entangled twin at an earlier moment. Imagine two entangled particles born from the same event flying apart at nearly the speed of light. They are a single system eternally connected. We know that if we measure a property of one, say its spin, its twin, no matter how far away, will instantly adopt a correlated spin. The mystery has always been how that information travels faster than light. Retrocausality offers a terrifyingly elegant, yet deeply unsettling solution. It suggests no information travels faster than light at all. Instead, the act of your measurement, your choice here and now, sends an influence backward in time to the moment the particles were created. This influence then travels forward in time, with each particle presetting their properties, so that when they are eventually measured, they appear perfectly correlated. The event in your future, your measurement, becomes part of the cause of an event in their past. The timeline becomes a loop. The neat linear progression of cause and effect is replaced by a complex interwoven tapestry where past, present, and future are in a constant, subtle dialogue. This is not a fringe fantasy. This idea emerged from the very heart of quantum mechanics, from the unresolved puzzles posed by its founders. It was championed by brilliant physicists like John Archibald Wheeler, a collaborator of Einstein and a true titan of 20th century science. He conceived of thought experiments so profound they continue to challenge us today, experiments that seem to show that a choice made by an observer in the present can determine the path a photon took billions of years ago. It's as if the universe holds its breath, waiting for a decision to be made in the far future before it commits to a version of the past. The implications are staggering, bordering on the philosophical and the spiritual. If the future can whisper back to the past, what does that say about the nature of reality itself? Is the universe not a story being written, but a story already finished? A complete four-dimensional block of space-time that we are merely experiencing slice by slice? A cosmic sculpture that exists in its entirety, whose end is just as real and concrete as its beginning. This concept forces us to confront the deepest questions of existence. Does it eliminate free will, suggesting our choices are not our own but are simply fulfilling a destiny required by a future event? Or in a more bizarre twist, does it elevate our consciousness to a cosmic level, implying that our present actions are so fundamental they can impress themselves upon a very fabric of history? It's an idea that many physicists find deeply disturbing. It feels like a cheat, a violation of a sacred trust we have with the cosmos. It opens the door to paradoxes that tie our logic in knots. If a future event can cause a past one, could one construct a scenario that prevents that future event from ever happening, thus creating a nonsensical, self-negating loop? This is the infamous grandfather paradox writ small on the quantum canvas. Yet the mathematics of quantum theory, the cold, hard equations that have proven more successful than any other scientific theory in history, do not explicitly forbid it. In fact, some interpretations seem to welcome it, offering it as a potential solution to some of the theory's most enduring enigmas, like the measurement problem and the nature of entanglement. Retrocausality challenges us to imagine that the universe is not a series of dominoes falling in a line. Instead, it might be a vast, intricate web, where pulling on a thread here in the present doesn't just tug on the future, but can also send a shiver backward, tightening a knot in the distant past. It asks us to consider that the flow of time might not be a fundamental property of reality, but an emergent one, an illusion born from our macroscopic perspective, like the smoothness of water that hides the chaotic dance of its individual molecules. We are large, complex systems governed by the laws of thermodynamics, where entropy, the measure of disorder, always increases. For us, the glass always shatters, it never reassembles. This creates a powerful, seemingly irreversible arrow of time. But for a single lonely particle adrift in the quantum realm, the rules of entropy may not be so binding. For that particle, time might be a two-way street. Our journey is to venture into this intellectual wilderness. We will walk the precipice of known physics and peer into the abyss of what we do not yet understand. We will explore the ingenious experiments designed to test this very notion, experiments that push technology to its absolute limits, trying to catch a glimpse of the future's influence on the now. We will speak with the physicists and philosophers who dare to entertain this extraordinary possibility, and with those who believe it represents a dangerous departure from rational science. We are not just exploring a scientific curiosity, we are confronting the very nature of our existence. Is causality the ultimate law, the cosmic anchor that keeps reality from dissolving into incoherent madness? Or is it merely a stubborn habit of the universe, a pattern that can be broken in its deepest, most hidden corners? The quest to find out takes us to the edge of space and time, to the beginning of the universe, and to the strange heart of the quantum world. We must let go of our most fundamental assumption and be prepared for an answer that could rewrite everything we thought we knew about the past, the present, and the nature of tomorrow. Imagine for a moment a single perfect arrow. For all of human history, for every life lived and every story told, we believed we understood its flight. It is launched from the bow of the past, soars through the fleeting moment we call the present, and lands unerringly in the target of the future. This is the arrow of time, and its one inviolable rule is the foundation of our sanity, the bedrock of our reality. An effect must always times follow its cause. A glass shatters only after it has fallen. A ripple expands only after a stone has pierced the water's surface. This sequence is not just a habit of the universe. To us, it is the universe itself. It's a law so deeply embedded in our consciousness that to question it feels like questioning our own existence. For centuries, our greatest minds didn't just accept this law. They built magnificent cathedrals of thought in its honor, turning an intuition into a physical and mathematical certainty. This grand construction began with a revolution not of politics or war, but of gravity and light. It was Sir Isaac Newton who first gave us the blueprint for this predictable cosmos. Before him, the heavens were the realm of gods and mystery, their motions guided by divine whim. But with his laws of motion and universal gravitation, Newton dismantled the celestial mystery and replaced it with a machine, a glorious, intricate, and utterly deterministic machine. We call it the clockwork universe. In this majestic vision, every star, every planet, every dust mote is a gear in a cosmic timepiece, wound up at the beginning of creation and left to tick along a predetermined path. If you could know the precise position and momentum of every single particle in the universe at one instant, a hypothetical intelligence that came to be known as Laplace's demon, you could in principle calculate the entire future of everything. And not just the future, you could also rewind the clockwork, calculating with perfect precision the entire unwritten history of the past. There are no surprises in this universe, no real chance, no genuine freedom. There is only the inexorable unfolding of a pre-written script, a chain reaction of cause and effect stretching from the dawn of time to its ultimate twilight. Your life in this Newtonian dream is simply one intricate series of falling dominoes. The choice you believe you made this morning was not a choice at all. It was the inevitable consequence of a cascade of events set in motion billions of years ago. The chemical reactions in your brain were simply following the same rigid laws that guide a planet in its orbit. This idea is both terrifying and strangely comforting. It suggests a universe of profound order, a place where everything happens for a reason because it simply could not have happened any other way. For over 200 years, this deterministic vision held sway. It was the supreme achievement of human reason, a testament to our power to decode the logic of the cosmos. Science was a project of filling in the details, of measuring the gears with ever greater precision. The fundamental principle that the arrow of time flies straight and true, and that the present is the simple and direct offspring of the past, was considered settled fact. The book of the universe was already written. Our job was merely to learn how to read it. But then another mind, arguably the greatest since Newton's, came along and revealed that the book was far stranger than we could have ever imagined. He didn't break the arrow of time. He forged it into something even more absolute. Albert Einstein, with his theories of relativity, did not dismantle Newton's clockwork. He revealed the very substance from which it was built. He showed us that space and time are not separate empty stages upon which the drama of the universe unfolds. Instead, they are woven together into a single dynamic fabric spacetime. This was a conceptual leap of breathtaking audacity. It meant that time itself was no longer a universal ticking clock, the same for everyone everywhere. It was a local personal experience, a river that could flow at different speeds depending on your velocity and the strength of the gravity you felt. An astronaut speeding through the cosmos would age more slowly than their twin on Earth. Time, the most constant thing we knew, was malleable. Yet in this strange new reality, the law of cause and effect became even more tyrannical. Einstein's universe is often described as a block universe. Imagine all of existence, every moment, from the Big Bang to the final distant end of time, laid out at once. It's not a story that's being written. It is a finished novel, a complete four-dimensional block in which the past, present and future all coexist simultaneously. You are not traveling times through time's time in this block universe. Your life is a static trajectory, a world line etched through the space-time block. Your birth is at one end of the line, your death is at the other, and every moment in between is a permanent, unchangeable part of the cosmic geometry. Just as the city of Rome is always there in its specific geographical location, your 5th birthday party is always there at its specific coordinate in space-time. We only times perceive time as flowing because our consciousness is traveling along this pre-carved world line. In this view, the future is no more uncertain than the past. We just haven't arrived there yet. And what enforces the sequence? What keeps the arrow of time pointing in one direction along this static path? The ultimate cosmic speed limit, the speed of light. Nothing, absolutely nothing, can travel faster through the fabric of space-time than light. This means an effect can never race ahead of its cause. An event happening here and now can only influence events within its future light cone, the region of space-time it can reach traveling at or below light speed. It is fundamentally impossible in Einstein's universe for you to receive a signal from your own future. The structure of space-time itself forbids it. Causality was now more than a law of physics. It was the very scaffolding of reality. By the turn of the 20th century, the edifice of classical physics seemed complete. We had a universe built on the unshakable foundations of Newton's mechanics and Einstein's relativity. It was a universe of majestic certainty of absolute laws, a place where every effect had a preceding and knowable cause. Physicists spoke of a theory of everything being just around the corner. We believed we had solved the great puzzle. We were, of course, catastrophically wrong. Because at the very same time, a group of scientists peering into the subatomic realm, the world of the impossibly small, were discovering that the foundations of our reality were not made of solid rock at all. They were made of smoke and mirrors and paradox. They had stumbled into a looking-glass world where the fundamental rules of cause and effect, the very arrow of time, seemed to bend, to fray, and perhaps even to break entirely. This was the dawn of quantum mechanics, and it began not with a thunderous explosion, but with a quiet, baffling whisper. A whisper that suggested a single particle could be in two places at once. The first crack in the classical facade was a phenomenon known as wave-particle duality. In our everyday world, things are simple. A thrown baseball is a particle. It exists in one definite location at any given time. The ripples in a pond are waves. They are spread out, diffuse, and can interfere with each other. The two concepts are mutually exclusive, but in the quantum realm, this distinction dissolves into a bewildering fog. An electron, one of the fundamental building blocks of our world, refuses to be so easily categorized. Sometimes it behaves exactly like a tiny solid bullet, a particle. At other times, it behaves precisely like a smeared-out wave of probability, a ghostly ripple of potential existence. This was first and most famously demonstrated in the double-slit experiment, an experiment so simple in its design and so profound in its implications that it has been called the heart of quantum mystery. The setup is straightforward. You fire a stream of electrons one by one towards a barrier with two thin parallel slits cut into it. Behind the barrier is a detector screen that records where each electron lands. If an electron is a simple particle like a tiny grain of sand, the outcome should be obvious. Each electron will pass through either the left slit or the right slit, and you'll end up with two distinct bands on the screen behind the barrier, mirroring the two slits. Simple cause and effect, but this is not what happens. When you run the experiment and simply let the electrons fly, what appears on the screen is not two bands, but a complex pattern of many bands, an interference pattern. This is the unmistakable signature of a wave. It's the same pattern you would get if you sent water waves through the two slits. The wave fronts passing through each slit would interfere with each other, creating peaks and troughs, crests and valleys. But how can this be? We are sending the electrons one at a time. A single electron, acting as a wave, must somehow pass through times, both times slits simultaneously interfering with itself before recombining to strike the screen at a single point. It's as if each particle is aware of the entire experimental setup, exploring all possible paths at once. The particle, it seems, is nowhere and everywhere until it is somewhere. This is where the story takes a turn for the truly bizarre. The experimenters, naturally baffled, decided to find out which slit each electron was times going through. They placed a tiny detector at the slits, a miniature sentry designed to watch the particles as they passed. A perfectly reasonable thing to do. And the moment they tried to observe the electron's path, the interference pattern vanished. Instantly. What appeared on the screen was exactly what classical intuition predicted all along. Two simple bands right behind the two slits. It was as if the electrons times knew times they were being watched. The very act of measuring which path the electron took forced it to choose a path to abandon its ghostly wave-like nature and behave like a well-behaved, respectable particle. Remove the detector and the interference pattern returns. The electron once again goes back to being a wave passing through both slits at once. Think about the implications of this. The reality of the electron's state, whether it is a wave spread across all possibilities or a particle on a single definite path, seems to be determined by the final act of measurement. The effect our observation appears to reach back and define the nature of the cause, the electron's journey. The solid objective reality of Newton and Einstein was melting away, replaced by a participatory universe where the observer was not a passive spectator, but an active creator of what is real. This unsettling discovery led directly to one of the deepest and most persistent puzzles in all of science, the measurement problem. Quantum mechanics describes the unobserved world with a beautiful mathematical tool called the wave function. This wave function represents not a concrete reality but a cloud of possibilities. An unobserved electron isn't times at times a specific location. Its wave function describes the probability of finding it at every possible location. It exists in a state of superposition, a ghostly blend of all its potential realities. But the moment we measure it, the moment we look, this cloud of possibilities instantly collapses into a single, definite reality. The electron suddenly appears at one specific spot. The question that has haunted physicists for a century: is this what exactly constitutes a measurement? What is the magical ingredient in an act of observation that can tame the quantum ghost and force it to become solid? Is it the interaction with a large, complex piece of equipment? Does it require a conscious observer, a human mind, to collapse the wave function? Or does the universe itself split into infinite parallel worlds with every quantum interaction? One for each possible outcome. We still do not have a consensus answer, but what is clear is that the simple linear chain of cause and effect is broken. In the classical world, you measure a property that already exists. A planet has a position and we measure it. The measurement reveals a pre-existing fact. In the quantum world, it seems the property does not exist in any definite sense, times, until times it is measured. The act of measurement itself appears to be an act of creation. It doesn't just report the past, it seems to solidify it from a mist of potential. The firm line between cause, the state of the particle, and effect, our knowledge of it, becomes hopelessly blurred. It's a profound challenge to our very conception of existence. It suggests that before an observation is made, the universe is a shimmering sea of potential, and our interaction with it is what crystallizes the single reality we experience. We are not just living in the universe, we are in some deep and mysterious way bringing it into being moment by moment. But even this profound challenge to our understanding of reality would be overshadowed by an even stranger quantum phenomenon, a discovery so utterly counterintuitive that it would shake Albert Einstein to his very core and make him question if the theory he helped create could possibly be complete. He called it spooky action at a distance. Today we call it quantum entanglement. It represents the most radical departure from our classical way of thinking, a direct assault on the idea that an object can only be influenced by its immediate surroundings, a principle known as locality. Imagine you have two subatomic particles that are created together in a special interconnected state. They are now entangled. You can separate these two particles, sending one to the other side of the laboratory or to the other side of the galaxy. The strange connection between them remains unbroken by time or distance. According to quantum mechanics, certain properties of these particles, like their spin, remain in a state of superposition, an undecided 50-50 chance of being up or down until one of them is measured. The moment you measure the spin of particle A and find it to be up, you know instantly and with absolute certainty that its entangled twin particle B, no matter how far away it is, has just collapsed into a state of spin down. It's not that particle B times had times a spin down state all along that you've just discovered. Before the measurement, its spin was genuinely undefined. The act of measuring particle A instantly determined the reality for particle B faster than the speed of light. This instantaneous connection, this seeming violation of Einstein's cosmic speed limit, horrified him. It felt like a form of cosmic telepathy, a cheat that broke the fundamental rule that no influence could travel faster than light. He was convinced it pointed to a flaw in quantum theory, a hidden variable that we simply hadn't discovered yet. But experiment after experiment has proven that Einstein was wrong. This spooky action is real. The universe is non-local. It is a place where two points in space-time can be profoundly connected, their fates linked in a way that defies our everyday intuition about space and separation. While it's true that this connection cannot be used to send a meaningful message faster than light, and therefore doesn't technically violate causality, in that sense it shatters the classical worldview in a more fundamental way. It tells us that the universe is not a collection of individual isolated things. It is a single, indivisible whole, an intricate web of relationships where touching one part can instantly ripple across the entire tapestry. And so, by the mid-20th century, the beautiful, orderly clockwork of classical physics lay in ruins. In its place stood a strange and shimmering new reality, one governed by probability, uncertainty, and ghostly connections. Our comfortable, intuitive understanding of cause and effect had been mortally wounded by a series of unsettling revelations. We had discovered that the fundamental nature of reality might not be fixed until it is observed. We had learned that the very act of observation, the effect, seems to be a crucial ingredient in creating the cause, and we had found that connections can exist across the cosmos that seem to operate outside the normal constraints of space. The arrow of time, once so straight and true, now flew through a quantum fog. The old rules were broken. A new set of rules had emerged, rules that were bizarre and paradoxical, but undeniably true. This left science with a tantalizing and deeply disturbing question. If the quantum world could so thoroughly defy our intuitions about reality, about objects, and about space, could it also be hiding one final, ultimate secret? Could it defy our deepest intuition of all, the one that says the past is fixed, the future is yet to come? If an effect can define its cause, at the moment of measurement, could an effect in some strange way reach back and truly times precede times it, and so we leave the comfortable shores of the predictable world behind? Our journey has brought us to the edge of an abyss, a place where the fundamental pillar of our reality, the steadfast law that a cause must always precede its effect, begins to crumble under the weight of observation. This is no longer a philosophical debate held in quiet halls of academia. This is the front line. The confrontation begins here in the cold, hard light of experiment, where the universe is forced to answer our most impertinent questions. We are about to witness phenomena so profoundly strange they feel less like physics and more like a form of cosmic magic, a magic that seems to unravel the very fabric of time. Our first guide into this bewildering territory is one of physics' great visionaries, John Archibald Wheeler, a man who saw the universe not as a machine but as a participatory, still unfolding story. He devised a thought experiment so audacious, so grand in its scale, that it uses the entire cosmos as its laboratory bench. He asked us to imagine a photon, a single particle of light beginning a journey from a quasar unimaginably far away, an island of furious energy in the dawn of time. This photon has been traveling for billions of years, a lonely messenger crossing the expanding void. On its path towards us, towards our telescopes on Earth, it encounters a colossal object, an entire galaxy. The immense gravity of this galaxy acts as a lens, a gravitational anchor so powerful it bends the space-time around it. This cosmic lens captures our lone photon and offers it a choice. It can travel around the left side of the galaxy, or it can travel around the right. From our classical intuitive standpoint, the photon must choose. Like a traveller at a fork in the road, it must commit to one path. Now we set up our observation on Earth billions of years later. We have two options for how we wish to receive this ancient light. In the first scenario, we place two separate telescopes, one aimed precisely at the path from the left side of the lensing galaxy, the other aimed at the path from the right. We wait. Eventually, one of our telescopes registers a click. A single photon has arrived. If the left telescope clicks, we know with absolute certainty the photon took the left-hand journey around that ancient galaxy. If the right one clicks, it must have taken the right-hand path. The situation is simple, unambiguous. We have asked the photon a which path question, and it has answered. It behaved like a well-behaved particle, a tiny bullet, that followed a single discrete trajectory through the cosmos. This is exactly what our intuition and all of classical physics would predict. But Wheeler, with a twinkle in his eye, invites us to make a different choice. In the second scenario, just moments before the photon is due to arrive, we decide to do something utterly bizarre. We remove our two separate telescopes. In their place, we insert a device known as a beam splitter. This is essentially a half-silvered mirror, a quantum gatekeeper. It's designed to take the light arriving from both the left and right paths and recombine them, directing them towards a single screen or detector array. We are no longer asking which path the photon took. Instead, we are asking the universe to show us what happens when the times possibility, times of both paths, is allowed to interfere. By recombining the paths, we are giving the photon a chance to interfere with itself, a definitive hallmark of a wave. A particle cannot be in two places at once, but a wave can. A wave rippling through the cosmic ocean could indeed travel both paths simultaneously, like a wave splitting around a rock in a pond, only to meet itself again on the other side. When these two wavefronts meet, they will create an interference pattern, a characteristic series of bright and dark bands. The bright bands appear where the crests of the waves add up, and the dark bands where a crest meets a trough, cancelling each other out. And when we perform this experiment, that is precisely what we find. An interference pattern emerges, built up one photon at a time. This pattern is incontrovertible proof. The only way it can form is if our single photon did not choose a path. It acted as a wave, travelling both routes around that galaxy at once, exploring the cosmic map in its entirety before reaching our detector. Here now you must hold your breath. The paradox, the ghost in this cosmic machine, is about to reveal itself. The critical element in Wheeler's delayed choice experiment is the word delayed. The choice of which experiment to perform, whether to set up two telescopes to determine the path, or to use the beam splitter to check for interference, is a choice we make. And we make it on Earth in the present moment. The photon, however, had to pass that distant lensing galaxy billions of years before life even emerged on our planet. The moment of its alleged decision to be a particle and take one path, or to be a wave and take both, happened in the deep primordial past. Yet our observation times seems to determine the nature of that ancient event. If we put up the telescopes, we find that the photon travelled as a particle. It chose a single path billions of years ago. If at the very last nanosecond we swap in the beam splitter, we find the photon traveled as a wave, taking both paths billions of years ago. It's as if the universe holds its breath for eons, refusing to collapse the photon's reality into a definite state until a conscious observer billions of years in its future decides which question to ask. Our decision, made in the here and now, appears to reach back in time and dictate the physical history of a particle in the distant past. The rigid spine of causality, the sacred timeline of history, has been fractured. The effect our measurement is now, the cause it seems to be influencing, is buried under billions of years of cosmic dust. This single elegant thought experiment, now confirmed by real-world laboratory tests, throws open a door we never knew existed, a door that seems to lead directly into the past. But if this cosmic-scale experiment cracks the foundation of time, the next step in our investigation demolishes it completely. We move from the theoretical grandeur of the cosmos into the controlled precision of the lab, to an experiment so audacious, so profoundly mind-altering, it has been called the ultimate quantum heist, the quantum eraser. It takes Wheeler's delayed choice and adds another almost cruel layer of complexity. It asks a terrifyingly simple question: what if we could learn which path a particle took, and then after the fact choose to times erase times that knowledge? Could we retroactively restore the wave-like behavior of a particle that has already finished its journey? The setup for this experiment is a masterpiece of quantum engineering. It begins with a special crystal which has the peculiar property of being able to take a single high-energy photon and split it into two new lower-energy photons. Crucially, these two photons are entangled. They are quantum twins born from the same event, and their fates are now inextricably and instantaneously linked. Whatever happens to one is immediately reflected in the state of the other, no matter how far apart they may travel. We will call them the signal photon and the idler photon. Their connection is our secret key to manipulating the past. The signal photon, our primary subject, is sent on a journey towards a screen. On its way, it encounters a classic double-slit barrier. Just like in Wheeler's experiment, this presents a choice. It can go through the top slit, or it can go through the bottom slit. And just as before, if we don't know which slit it traverses, it will behave as a wave passing through both at once, creating an interference pattern on the screen behind it. But this time we are going to cheat. We place cunningly designed polarizers and detectors right at the slits. These devices allow us to record with 100% certainty which slit the signal photon passed through. We are actively gathering which path information, and the moment we do that, the quantum rules are clear. The wave behavior vanishes. The superposition collapses. The signal photon now behaves like a simple particle. It hits the screen as a single dot, contributing to one of two distinct clumps of light, one behind the top slit, one behind the bottom. There is absolutely no interference pattern. We have sacrificed the mystery of the wave for the certainty of the particle. So far, this is standard quantum mechanics. But we haven't accounted for the other twin, the idler photon. While the signal photon completes its short journey to the screen, its entangled partner, the idler, is sent on a much longer meandering path. Think of it as taking the scenic route. This delay is critical. The idler photon is our quantum informant. Because it is entangled with the signal photon, it carries a secret copy of the which path information. If the signal photon went through the top slit, the idler photon carries a signature of that event. If the signal photon went through the bottom slit, the idler carries that signature instead. The idler is the getaway car carrying the evidence of the crime. Long after the signal photon has already landed on its screen, its position recorded, its fate seemingly sealed as a particle, the idler photon finally arrives at its own destination. And here at the end of its journey, we, the experimenters, are faced with a choice. This is the eraser part of the experiment. We have set up an elaborate array of beam splitters and detectors for the idler. Depending on how we route the idler photon into this system, we can choose to do one of two things. Option 1, we can measure the idler in a way that preserves the which path information. We can determine from the idler whether its twin went through the top or bottom slit. We are choosing to times read times the evidence. Option 2, we can send the idler through a series of beam splitters that effectively scramble or erase the which path information. After passing through this quantum eraser, it becomes fundamentally impossible to know which path its signal twin took. We have chosen to times destroy times the evidence. And remember, this choice is made times after times the signal photon has already finished its journey. Its impact location on the screen is a done deal, a piece of recorded history. Now for the revelation that defies all logic. The experiment is run, and thousands upon thousands of photon pairs are recorded. We look at the data from the signal photons on their screen. At first glance, it looks like a random scattershot, two broad clumps of dots, exactly what you'd expect for particles with no interference whatsoever. The history of these particles seems fixed. But now we perform a final devastating act of data analysis. We go back through our records and look only at the signal photons whose idler twins we later chose to send into the eraser. We isolate just that subset of data, ignoring all the others, and as we filter the results, something impossible happens. The chaos organizes itself. Out of the random noise, a ghostly interference pattern emerges, the signature of a wave. It's as if these specific signal photons, which we had confirmed were particles when they passed the slits retroactively, knew that their witch path information was times going to be times erased in the future. Knowing this, they behaved as waves, interfering with themselves to create the pattern. Now consider the other set of data. We look at the signal photons, whose idler twins were measured in a way that times preserved, times the witch path information. For this group, nothing changes. They remain as two distinct clumps, no interference pattern, ever. These photons behaved as particles because their history was destined to be known. Let the weight of this sink in. An action you take in the present, the choice to erase information from the idler photon, reaches back and alters a pattern of events that has already concluded. The data from the signal photons already stored on a hard drive reconfigures itself based on a future measurement. It is a direct, unavoidable confrontation with the notion that the past is fixed. The experiment strongly suggests that the physical reality of a particle is not a settled fact until all possible information about it anywhere in the universe has been fully resolved. The universe's bookkeeping, it seems, is not closed until the final entry is made, and that final entry can redefine all the ones that came before. What is the mechanism for such a ghostly link across time? The answer lies in that strange connection we mentioned, the foundational quantum mystery that Einstein himself could never accept entanglement. This is the quantum telephone line, the invisible thread that allows for this temporal paradox. When our crystal creates the signal and idler photons, it doesn't just create two particles. It creates a single, unified system described by one wave function, even when the particles are separated by vast distances. Think of it not as two separate coins, but as a single coin spinning in the void, which only reveals its two opposite faces, heads and tails, when a measurement is made. Before that measurement, it is neither heads nor tails, but a shimmering haze of both potentials. This connection is not bound by the classical speed limit of the universe, the speed of light. It is instantaneous. If you measure one entangled particle to be spin up, you know in that exact same moment that its partner, even if it's on the other side of the galaxy, must be spin down. No information has traveled between them in the conventional sense. You cannot use this to send a message faster than light. Instead, you have simply revealed a pre-existing but previously indefinite correlation. It's a shared state of being, a quantum pact that transcends space. The quantum eraser experiment leverages this timeless, spaceless connection. The signal photon and the idler photon are part of one indivisible system. The witch path information doesn't truly exist in one place. It exists within the correlation of the entire entangled system. When we measure the signal photon at the slits, we are only looking at half the story. The system's full reality is still in flux, still in superposition. The final, definitive state of that system, whether it contains discernible path information or not, is not locked in until the very last measurement is performed on any part of it. When we choose to erase the information from the idler photon, we are performing the final act in this quantum drama. We are collapsing the entire entangled system into a state where no path information exists. And because the system is a single entity that transcends time, this final measurement defines its nature throughout its entire history, from the moment of its creation to the moment of its detection. It doesn't send a signal back in time. It establishes a single consistent story for a system that was until that final moment fundamentally ambiguous. We stand here now confronted by the evidence. Wheeler's cosmic experiment suggests that our present choices can echo into the deep past. The quantum eraser demonstrates it with chilling, repeatable precision in the laboratory, and entanglement provides the ghostly mechanism, the non-local connection that seems to ignore the familiar boundaries of both space and time. The sacred law of cause and effect, once the bedrock of all science, the most fundamental rule of our experience, now appears to be nothing more than a local ordinance, a guideline that the universe enforces in our classical world but casually disregards in the quantum deep. The evidence is on the table, the clocks are broken, the arrow of time is no longer a straight, inexorable flight into the future. It appears to be a tangled, shimmering web. So what are we actually seeing? Is this a genuine glimpse of the future reaching its hand back to shape the past? Or are we staring into a mirror so profound, so alien that the ghost we see is merely a reflection of our own deep misunderstanding of time itself? The confrontation has left us with more questions than answers, forcing us to seek a new story, a new interpretation of reality that can somehow contain these impossible truths. And so we stand at an impasse, a precipice of understanding. The quantum world has shown us its impossible face, a reality where particles exist in ghostly superposition, where they are linked across galaxies by an invisible thread, and where a choice made times seems to reach back and alter what has already passed. The old rules, the comfortable sequential logic of our everyday lives, have shattered against the bedrock of the very small. We have been brought to our knees by paradox, forced to confront a universe that behaves less like a predictable machine and more like a lucid dream one, where the script seems to be written as the play is performed. The interpretations we have clung to for a century of collapsing waves, of hidden variables, of splitting universes, all seem to strain to add layers of complexity and mystery rather than offering true clarity. They feel like beautiful, intricate cages we have built around a truth that refuses to be confined. What if the problem isn't with the universe, but with our most fundamental assumption? What if the cage we must break is the most rigid one we know, the unyielding one-way arrow of time? To even consider this is an act of scientific heresy. It asks us to look at the very fabric of causality, the sacred principle that an effect can never precede its cause, and wonder if it is merely a local ordinance, a law that governs our macroscopic world but dissolves into whispers in the quantum realm. It is here, in this intellectual wilderness, that we find a small but defiant group of thinkers who proposed a breathtakingly radical solution. They suggest we stop trying to force the quantum world to obey our linear perception of time, and instead listen to what it has been telling us all along, that the past, present, and future are engaged in a constant dynamic conversation. To understand this conversation, we must meet its architect-physicist John Cramer. In the 1,980 seconds, wrestling with the same paradoxes that have haunted us, Cramer looked back at the very equations of quantum mechanics, the mathematical language of this strange world, and noticed something profound that had been largely ignored. The foundational equations of electromagnetism and quantum physics, when solved naturally, produce two sets of solutions. One describes a wave moving forward in time from a source to a destination exactly as we would expect. This is called the retarded wave, and it forms the basis of all our classical physics. But there is always another perfectly valid mathematical solution, a wave that travels backward in time from the future to the past. This advanced wave has historically been dismissed as a mathematical quirk, a physically meaningless anomaly that we discard because, well, things don't happen backward. But Cramer asked a question of stunning simplicity and staggering implication. What if nature uses times both times? What if the universe is not throwing away half of its own rulebook? From this single audacious question, the transactional interpretation of quantum mechanics was born an idea that doesn't just solve the quantum paradoxes, it recasts the entire universe as a story written collaboratively by the future and the past. Imagine an atom poised to release a photon of light. In the standard view, this is a moment of random, unpredictable decay. The atom simply emits a particle in a particular direction, but in Kramer's vision, something far more intricate and elegant unfolds. The atom does not just shout into the void, it whispers a question to the entire universe. This is the offer wave. It radiates outward from the emitter, in all possible directions, moving forward in time at the speed of light. This wave is not the photon itself. It is a ghost of a photon, a wave of pure potential carrying the blueprints of energy and momentum. It is a query sent to the future, asking, is there anywhere out there that can accept me? This wave of possibility spreads through the cosmos, washing over everything in its path, continuing its search for a home. It is the universe exploring every what-if. Now picture the potential destinations for this energy. Across the laboratory or across the void of space, there are countless other atoms, what we call absorbers. These are particles capable of receiving that exact quantum of energy. When the offer wave from our emitter reaches one of these potential absorbers, it prompts a response. But this is where our intuition must completely give way to the quantum strangeness. The absorber, upon receiving the offer from the past, sends a reply not into its own future, but back into its past. It generates its own confirmation wave, an echo that travels backward in time, retracing the exact path of the offer wave it just received. This confirmation wave is a message sent from the future to the past, a signal that says, yes, your offer is accepted, I am here. Every potential absorber that receives the offer wave sends its own confirmation wave, hurtling back through time toward the original emitter. The emitter is now in its own present moment, receiving a cascade of echoes from its own future. It sent out one question and is getting back a chorus of potential answers from all the places its energy could have gone. So how is a choice made? How does this symphony of potential futures resolve into a single concrete reality? This is the heart of the transaction, the handshake across time. The emitter, in a process akin to a resonant feedback loop, strengthens the connection with the confirmation wave that is strongest and most perfectly in sync with its original offer. It's a cosmic negotiation. The forward-traveling offer wave and the backward-traveling confirmation wave interfere with each other. Along the single path connecting the emitter to that one specific absorber, the two waves reinforce each other, creating a standing wave of amplified probability. Everywhere else, for every other potential path, the waves cancel each other out, fading into nothingness. This handshake, this amplified resonance between a single question from the past and a single answer from the future, is what forges reality. It is in this atemporal moment of agreement that the transaction is completed. The transfer of energy becomes real. The photon is born, and we perceive it as a particle that has traveled a single definite path from the emitter to that one chosen absorber. All other possibilities, all the paths not taken, were never truly real. They were simply failed negotiations, unanswered questions, whose echoes faded before they could be confirmed. The randomness we perceive in quantum mechanics is in this interpretation the result of a complex bidding war between potential futures, a war whose outcome is determined not in the present alone, but in a dialogue that spans time. This isn't just a metaphor, it's a model that claims to describe the literal physical process by which quantum events unfold. It replaces the mysterious collapse of the wave function with a tangible, if deeply strange physical mechanism, a completed transaction. Let us now take this radical new lens and turn it back toward the scene of the crime, the double-slit experiment that has confounded generations. In our previous exploration, a single particle seemed to magically know whether one or two slits were open, traveling as a wave through both and as a particle through one. But how could it know? The transactional interpretation offers a startlingly direct answer. The particle itself never knows anything. The transaction does. When the electron is emitted, it sends its offer wave forward in time toward the two slits. This wave of potential, behaving as all waves do, passes through both slits simultaneously. It then continues on toward the detector screen behind them. Every single point on that screen is a potential absorber, a possible future for our electron. Each of these points, upon receiving the offer wave, sends its confirmation wave backward in time. These confirmation waves travel from the screen back through both slits and return to the emitter in the past. Now the crucial handshake occurs. The interference isn't just happening at the screen. The entire transaction, the interplay between the offer and confirmation waves, creates the interference pattern. The bright bands on the screen are the locations where the handshake is strongest, where the offer and confirmation waves constructively interfere, completing the transaction and allowing a real electron to appear. The dark bands are where the transaction fails, where the waves destructively interfere and no electron can ever land. The particle doesn't go through one slit or the other. Its reality is forged by a completed transaction that encompasses both times paths through space-time simultaneously. But what happens when we try to watch? What happens when we place a detector at one of the slits to see which path the electron takes? The moment we do, the interference pattern vanishes and the wave behavior is lost. For decades, this was attributed to the act of observation, as if the universe were camera-shy. TIQM provides a concrete physical explanation free of any mystical observers. The detector you place at one slit is now a new, very tempting potential absorber. It is much closer to the emitter than the screen is. When the offer wave reaches this detector, the detector immediately sends a powerful confirmation wave back in time. Because it is so close, its confirmation arrives back at the emitter far more quickly and strongly than any confirmation from the distant screen. It effectively wins the cosmic negotiation. The handshake is completed not with the screen but with the detector at, say, the right-hand slit. A transaction is finalized emitter to right slit detector. Because this transaction is now the one and only reality for that electron, the entire part of the offer wave that went through the left slit and all the potential transactions with the screen that would have resulted from it are cancelled, out. They become failed bids. The interference pattern, which relied on the possibility of both times paths being part of the final transaction, can no longer form. The electron materializes at the one slit where its journey was confirmed. The future, in the form of your decision to place a detector, has reached back in time and determined the electron's past behavior. It's not consciousness causing collapse, it's causality, a causality that flows in two directions. This powerful framework becomes even more compelling when we confront the truly bewildering quantum eraser experiment. This is the experiment that seems to defy all logic, where information gathered about a particle's path can be erased. Times after times, the particle has already hit the screen retroactively, restoring its wave-like interference pattern. How can a future event possibly unring a bell in the past? Within the transactional interpretation, this isn't a paradox at all. It's the expected outcome of a temporal dialogue. Let's follow the transaction. A photon is fired. Its entangled twin heads toward a set of detectors, which will reveal which path information. The first photon, meanwhile, has already passed the slits, and its position has been recorded. According to standard logic, its fate is sealed. It either contributed to an interference pattern, or it did not. But in TIQM, the transaction is not yet complete. The full story isn't written until all times potential absorbers have had their say. The offer wave from the original emitter encompassed the entire experimental setup. The confirmation waves, the echoes from the future, will come, not just from the first detector screen, but from the final resting place of the entangled twin particle as well. If you make a measurement on that twin that preserves the witch path information, the confirmation wave sent back through time from that measurement will reinforce a particle-like history. The handshake that is finalized will be one that includes definite path information, and thus no interference pattern is formed for the first photon. The transaction solidifies a classical particle-like reality. But if you choose to erase that information by routing the twin photon through a device that scrambles its path data, a completely different confirmation wave is sent back through time. This new echo from the future contains no witch path information. It carries the signature of wave-like ambiguity. This backward-traveling wave returns to the original emitter, and the resulting handshake it forms is one that includes both paths through the slits. The transaction that is completed is a wave-like one, and as if by magic, the interference pattern appears on the first screen, a pattern whose existence was dictated by a choice you hadn't even made yet when the photons first landed. The erasure is not a mystical act, It is you, the experimenter, deciding which confirmation wave the future will send back to the past, thereby selecting which quantum history becomes real. And finally, we arrive at the ghostliest of all quantum phenomena, entanglement, the spooky action at a distance that so troubled Einstein. Two particles linked in their creation remain perfectly correlated no matter how far apart they fly. Measuring the property of one instantly influences the property of the other faster than light could ever travel. TIQM dissolves this paradox not by breaking the speed of light, but by stepping outside of time altogether. When two entangled particles are created, the emitter sends out a complex offer wave that describes a correlated system, a single quantum question with two parts. Later, when you measure the first particle, say on Earth, that measurement device acts as an absorber. It receives part of the offer wave and sends a confirmation wave back in time to the moment of creation. However, this is only half of the handshake. The transaction cannot be completed yet because the offer wave requires a second absorber for the other particle, the one now flying toward a distant star. The first confirmation wave upon arriving back at the origin point effectively modifies the remaining part of the offer wave that is still traveling toward that distant particle. It's a tentative handshake. Later, perhaps years later, when the second particle is measured by a distant observer, that absorber also sends a confirmation wave back through time to the origin point. Only when both times confirmation waves have arrived back at the moment of creation can the full transaction be completed. The handshake is a three-way, or rather a four-way agreement: emitter to absorber 1 and emitter to absorber 2, all negotiated outside of linear time in a single atemporal event. The perfect correlation we see is not the result of a signal passing between the particles in space. It is the result of a self-consistent agreement that locks their properties into place at the moment of their shared creation, an agreement brokered by echoes from their separate futures. There is no spooky action times at a distance asterisk. There is only a completed transaction that spans space-time, respecting all the laws of relativity, because the influence isn't a physical thing traveling through space at all. It is a condition of the transaction's successful completion. With this, the theory presents a universe that is profoundly interconnected, not just through space, but through time. It paints a picture of reality as a vast, shimmering web of completed transactions where every single quantum event is a finalized pact between a proposal from the past and an acceptance from the future. This idea is both terrifying and beautiful. It challenges our deepest intuitions about the flow of existence and our place within it. It suggests the future is not a completely unwritten page, but that it has a kind of phantom presence capable of influencing the here and now. It doesn't mean the future is fixed. Rather, the universe allows a constant fluid negotiation between all possibilities. We have journeyed from the edge of paradox to a potential solution of breathtaking scope, one that reframes reality itself. But a beautiful story is not enough for science. An elegant theory must face the cold, hard light of experimental scrutiny. Can we test this? Can we devise an experiment that could catch one of these echoes from the future in the act? Is there any way to truly prove that the future is whispering back to the past, or will this profound and radical idea forever remain an interpretation, a ghost in the quantum machine, and so the solid ground of our understanding cracks open? The simple, comforting march of time from a fixed past to an open future is revealed not as a law of nature, but perhaps as a profound and persistent illusion. We are left suspended over a new and dizzying chasm, forced to gaze into the depths of a universe where the future is not a destination we are traveling towards, but a silent partner in the creation of our present. This realization changes everything, not just for physics, but for the very story we tell ourselves about who we are. It forces us to confront questions that resonate far beyond the sterile walls of a laboratory, questions that touch the deepest roots of our experience, our freedom, and our identity. Because if an effect can ripple backwards through space-time, if a particle's destiny can influence its history, then the clear one-way street of causality becomes a tangled two-way labyrinth. The arrow of time, that steadfast guide of our existence, hasn't just been bent. For all we know, it might be shattered. This isn't merely an intellectual puzzle. It is a direct challenge to our sanity. The moment we entertain the notion of a future influencing the past, a horde of paradoxes like ghosts from a nightmare, logic immediately rushes to the forefront of our minds. Looming largest among them is the most famous temporal demon of all, the grandfather paradox. You know the story. A time traveler journeys into the past and prevents their own grandfather from meeting their grandmother. Consequently, the traveler's parent is never born, and thus the traveler themselves is never born. But if they were never born, they could not have gone back in time to commit the act in the first place. The entire causal chain collapses into a screaming contradiction, a logical impossibility that rips the fabric of reality apart. For decades, this thought experiment has served as the ultimate gatekeeper, the primary argument against any form of time travel or backwards influence, a philosophical bulwark protecting the sanctity of a consistent history. If retrocausality were true in the way our science fiction has imagined it, then our universe should be littered with the wreckage of these impossible loops. It should be an incoherent mess of self-cancelling events. Yet the cosmos appears remarkably stable, consistent, and logical, but the quantum realm, as we have seen time and again, operates under a far more subtle and enigmatic set of rules. The retrocausality proposed by quantum mechanics may not be the sledgehammer of a time traveler, but something more akin to a ghostly whisper, a gentle, persuasive pressure. It doesn't seem to empower a conscious agent to rewrite history at will. Instead, it suggests a universe that conspires on a fundamental level to ensure its own self-consistency. Imagine not a single branching timeline that can be pruned or altered, but a vast shimmering web of possibilities. The transactional interpretation of quantum mechanics, for instance, offers a compelling way out of the paradoxical maze. It describes every quantum event not as a simple emission from the past, but as a complex handshake between the past and the future. An electron preparing to emit a photon sends out an offer wave forward in time. Potential absorbers in the future send back a confirmation wave backwards in time. A transaction, a real event, only occurs when these two waves meet, forming a consistent, closed loop across space-time. In this model, you could never go back to prevent your own birth, because the future where you exist is already sending confirmation waves back to the past, reinforcing the exact historical path that leads to your existence. The universe simply will not complete a transaction that results in a contradiction. Any potential future that creates a paradox is like an echo in a void. It sends back no confirmation, and so the past that would create it is never actualized from the infinite sea of quantum possibility. This is the essence of what physicists call the Novikov self-consistency principle applied to the quantum scale. It proposes that any event that exists in a region of spacetime with closed time-like curves must be self-consistent. History is a settled affair not because it is unchangeable, but because any potential change would self-annihilate, failing to form a consistent transactional loop. The future doesn't rewrite the past. It collaborates with it. It votes on which of the myriad possible pasts gets to be times the times past, and the only candidate that can ever win the election is the one that leads to the future that cast the vote. So the grandfather paradox dissolves. It becomes an impossibility not because of some cosmic law forbidding it, but because the very mechanism of retrocausal influence is one that inherently seeks and enforces coherence. The universe, it seems, has its own immune system against paradox. Yet in solving one great problem, we unleash another one that is arguably more profound, more personal, and infinitely more unsettling. If the future state of a system can influence its present behavior, then where does that leave us, the conscious observers who believe we are navigating the present through our own free will? Are the choices we make truly our own, or are we merely puppets, our strings, pulled by a future that has already, in some sense, happened? This is the ancient battle between free will and determinism, now recast in the strange new light of quantum physics. For centuries, the deterministic argument was rooted in the past. If we knew the position and momentum of every particle at the Big Bang, a powerful enough intelligence could in principle calculate every event that would ever follow, from the formation of a galaxy to the words you are hearing at this very moment. It was a universe of cosmic clockwork wound up at the beginning of time. quantum mechanics seemed to offer a way out. Its inherent randomness, its probabilistic nature, suggested that the future was not a foregone conclusion but a branching tree of possibilities, a garden of forking paths where our choices mattered. Retrocausality threatens to slam that door shut once more, but from the opposite direction. It suggests a new kind of determinism, a superdeterminism, where the universe is a single, self-consistent entity, a four-dimensional block of space-time where past, present, and future all exist with equal reality. In this block universe, our sense of flowing time is an artifact of our consciousness, a trick of perception. Our life is not a journey we are taking, but a complete story already written, and we are simply experiencing it page by page. The end of the book influences the beginning. The final chapter helps shape the words of the first. Our choices are not choices at all, but simply the playing out of a pre-existing, self-consistent script. The measurement we make in a laboratory, the one that seems to collapse the quantum wave function and birth reality, was never a free choice. The decision to measure and the outcome we get were both determined from the beginning of time, correlated with the state of the particle, in a way that creates the illusion of entanglement and spooky action at a distance. For many, this is a deeply chilling and unacceptable conclusion. It renders our struggles, our triumphs, our love, and our grief as nothing more than the unwinding of a cosmic tape. It makes us automatons in a play written by no one. But perhaps there is a middle ground, a more nuanced reality, where the whispers from the future do not dictate our actions, but merely shape the landscape upon which we act. Imagine you are lost in a vast, dense fog. Before you lie an infinite number of possible paths. You believe you are free to choose any of them. Now imagine that a faint, almost imperceptible warmth emanates from the paths that lead to safety, while a subtle chill drifts back from the paths that lead to a dead end or a cliff edge. This is the influence of the future. It doesn't force your hand. It doesn't scream a warning or block a path. You can still choose to walk into the cold. You are still the one taking the steps, but the probabilities are no longer equal. Your free choice is gently nudged, biased towards a successful outcome. The future doesn't eliminate your free will. It provides a context for it. It sculpts the probability space in which your consciousness operates. In this view, we are still the authors of our story, but we are writing on paper that is not entirely blank. The paper has faint watermarks, impressions left by the story's end, guiding our pen, suggesting a turn of phrase here, a plot twist there, ensuring the whole narrative holds together. This would mean that our intuition, those gut feelings and flashes of insight that seem to come from nowhere, might have a physical basis. They could be the faint quantum whispers from our own future, the integrated signal of countless successful and unsuccessful outcomes rippling back to inform the present moment. It's a staggering thought that the very act of making a decision is a process of resonating with our own potential futures. This entire conversation, however, is not happening in a vacuum. It is the heart of a fierce and ongoing battle within physics itself. For every physicist intrigued by the explanatory power of retrocausality, there is another who views it with profound skepticism, even hostility. To its detractors, it is an intellectual poison, a desperate measure to solve quantum paradoxes by sacrificing the most fundamental principle of science and sanity, that cause must always precede effect. They argue that causality is not just a law of physics, it is the bedrock of logic, the very framework that allows us to make sense of the universe. Without it, science itself becomes impossible. How can you conduct an experiment if the act of setting it up could be influenced by the result you haven't yet received? It seems to invite chaos to open the door to a world where nothing can ever be truly known because everything is, influencing everything else in a dizzying, impenetrable loop. These critics argue that retrocausality is a phantom, a mathematical ghost, born from taking the equations of quantum mechanics too literally. Perhaps they suggest the equations are simply incomplete. Perhaps there are other more sensible explanations for the universe's strangeness, that we haven't yet discovered new particles, hidden variables, or deeper principles that preserve the forward flow of time that we so viscerally experience. They contend that we should not be so quick to abandon the core pillar of our entire worldview just to solve a few quantum riddles. The price of retrocausality, they say, is simply too high. It is the price of reason itself. But the proponents of these ideas, a brave and growing minority, argue that the opposite is true. They claim that it is the stubborn adherence to our intuitive classical view of time that is holding physics back. They look at the bizarre implications of standard quantum theory faster than light, spooky action, the measurement problem, the seeming necessity of a conscious observer, or the mind-boggling extravagance of the many worlds interpretation, and they ask, is retrocausality really any stranger than these? In their view, backwards in time influence is not a complication, it is a simplification. It elegantly dissolves many of the most persistent quantum paradoxes with a single powerful, albeit deeply counterintuitive idea. It heals the schism between quantum mechanics and relativity. It restores a form of local reality to the universe, meaning that influences don't need to travel faster than light. They can simply take a detour through time. They argue that our discomfort with the idea is not a sign of its incorrectness, but a symptom of our own cognitive biases. Biases hardwired by evolution to survive in a macroscopic world where arrows fly forward and glass shatters after it falls. They challenge us to be brave enough to follow the mathematics wherever it leads, even if it leads to a place where our fundamental assumptions about reality must be dismantled. This is not just a debate about equations. It is a clash of philosophical visions, a struggle for the soul of physics. It is a conflict between those who believe the universe must at its core be rational in a way we can comprehend, and those who suspect it is rational in a way that our minds have not yet evolved to grasp. And so, we are left to wonder what it means to exist in such a universe. What does it feel like to be a creature of cause and effect, living inside a reality that may not be bound by that same rule? Our perception of the world is built on a linear story. First this, then that. The lightning flashes, then the thunder rolls. The seed is planted, then the flower blooms. This narrative structure is embedded in our language, our memories, and our models of the world. If retrocausality is real, then this entire narrative is a convenient fiction, a simplified user interface for a reality of unimaginable complexity. It implies that every atom in your body, every particle of air you breathe, is not just a point-like object moving forward through time. It is a nexus of temporal connections, a standing wave of possibilities resonating with its own past and its own future simultaneously. The universe is not a story being written one word at a time. It is a finished, self-consistent poem where the choice of the last word influenced the first and the first word gave meaning to the last. We are simply the act of the poem being read. This is a reality of profound and resonant interconnectedness, where every point in space-time is in subtle conversation with every other. The philosophical and theoretical implications are staggering, pushing the very limits of what we can imagine. The debates rage on, fueled by mathematics, intuition, and taste. But speculation and philosophy, no matter how profound, can only carry us so far. They can build beautiful, intricate models of what might be, but they cannot tell us what times is asterisk. The questions have been asked. The paradoxes have been confronted. The terrifying and beautiful consequences have been laid bare. Now the conversation must move from the chalkboard to the laboratory. Is there any way to test this? Can we devise an experiment so cunning, so precise, that it could catch the future in the act of whispering to the past? Is it possible to build a machine that could detect an echo from tomorrow? This is the ultimate challenge. Because if we could, it would be more than just another scientific discovery. It would be a fundamental revelation about the nature of everything, a moment that would forever divide human history into two eras, the time we thought we were moving into the future and the time we knew the future was also moving into us. And so the idea settles upon us. A proposition so elegant, so profoundly unsettling, it feels less like a scientific theory and more like a ghost story told in the precise, cold language of mathematics. That the future might not be a distant, unwritten shore towards which we helplessly drift, but an active participant in the here and now, reaching back through the quantum foam to gently nudge the present. But physics, in its relentless pursuit of truth, is not a discipline of stories. It is a discipline of evidence. An idea, no matter how compelling, remains a ghost in the machine until it can be cornered, interrogated, and forced to confess its secrets under the harsh glare of empirical test. For science to accept a revolution that would shatter the bedrock of causality, it demands more than elegant equations. It demands a body. It demands proof extracted from the very fabric of reality within the sterile, shielded confines of the modern laboratory. This is the story of that hunt. A quest taking place at the absolute frontier of human knowledge, where scientists are building machines not to see farther into space, but to listen for a whisper from the future. The central challenge is almost diabolical in its complexity. How do you design an experiment where an influence from the future is the only times possible explanation for what you see? You must construct a perfect causal trap, a fortress of logic and engineering so impeccably sealed that no conventional forward-flowing explanation, no matter how strange, can sneak through its walls. The experiments of today are the direct descendants of Wheeler's delayed choice, but they have evolved into marvels of technological sophistication designed to close every conceivable loophole. Imagine once again our single photon on its journey. But now the choice of whether to measure its wave-like or particle-like nature is not made by a human, but by a quantum random number generator. This device is a crucible of pure chance, its output governed by the fundamentally unpredictable decay of a radioactive atom. The decision it makes is by the laws of physics as we know them, causally disconnected from anything that came before it. It is an island in time. The generator is placed light years away from the initial part of the experiment, ensuring that no signal traveling at the universe's maximum speed limit could possibly inform the photon about the choice that times will times be made. Yet, in these advanced setups, the experiment is taken a step further into a realm of even greater strangeness. Scientists now attempt to subtly influence the times random number generator itself, times moments after it has made its decision, and after the photon's fate has already been recorded. They aren't trying to change the past measurement of the photon. That is impossible. They are looking for something far more ephemeral, a ghost in the statistical data. They are testing whether this later action, this nudge on the decider, can retroactively correlate with the supposedly random choice that was made moments before. It's as if by pushing on the effect you could create a faint statistical echo in its cause. The physicists are not searching for a loud proclamation from tomorrow. They are not expecting a message spelled out in flashing lights, a clear violation of grandfather paradoxes. The models of retrocausality predict that nature cleverly conspires to prevent such paradoxes, to keep the causal chain on a macroscopic level intact. The influence is expected to be a whisper, not a shout. What they hunt for is a statistical tilt, a slight inexplicable bias in the torrent of data collected over millions upon millions of trials, a tiny deviation from perfect randomness that should not be there. It would look like the quantum random number generator, for no discernible reason, showed a minuscule preference for one outcome over another, a preference that perfectly correlates with the action the experimenters took. Times after times the choice was made. It would be as if the particles in their quantum uncertainty possessed a fleeting premonition, a subtle hunch about the measurement that was yet to come, and adjusted their random behavior accordingly. This is the fingerprint of the future. An echo arriving before the sound. To achieve this requires a level of precision that is almost unimaginable. Laboratories are buried deep underground to shield them from the faint rumble of cosmic rays. Optical tables floating on cushions of air cancel out the slightest terrestrial vibration. Lasers cooled to near absolute zero must be so stable that their beams do not waver by more than the width of an atom over vast distances. Every potential source of environmental noise, every stray magnetic field, every temperature fluctuation must be ruthlessly identified and eliminated, because the signal they are looking for, this faint whisper from tomorrow, is so delicate that it could easily be mistaken for or drowned out by the mundane noise of the present. You are in essence trying to photograph a phantom you can only perceive in a statistical mirror, and you must first prove that the mirror itself is flawless. This is where the scientific community splinters. For every visionary physicist designing these causal crucibles, there are 100 others who argue they are chasing shadows on the cave wall. The skepticism is not born of a lack of imagination, but of a deep and abiding respect for the scientific method. The critics argue that quantum mechanics is already a gallery of horrors for our classical intuition. Why invoke a backward-flowing river of time when other, more conventional, if equally bizarre explanations might suffice? Perhaps the statistical anomalies, if found, are not evidence of retrocausality at all. They could be the result of a subtle, undiscovered form of classical communication between the components, a loophole the experimenters failed to close. Or they could be an artifact of superdeterminism, the unsettling idea that everything in the universe, including the experimenter's choice, was preordained from the Big Bang, creating an illusion of correlation without any actual influence. A more common counterargument lies within the very interpretation of quantum mechanics itself. Proponents of the many worlds interpretation, for instance, would argue that there is no mystery to solve. In their view, every quantum measurement splits the universe. The photon behaves as both a wave and a particle, because in one branching reality it is measured as a wave and in another as a particle. There is no need for an influence to travel backward in time to inform the photon, because all possibilities are made real in an ever-expanding multiverse. The debate, therefore, is not just about experimental results. It is a battle for the soul of physics, a fundamental disagreement about the nature of reality itself. Is the universe a single unfolding story where the future can cast its shadow backward, or is it an infinitely branching tree of possibilities where every story is told simultaneously? Distinguishing between these interpretations is the grand challenge. An experiment must be designed not just to see an effect, but to prove that only one explanation, retrocausality, can account for it. This has led to a new vanguard of theoretical and experimental work, pushing beyond the delayed choice paradigm. Physicists are now exploring systems of multiple entangled particles, creating complex causal networks. Imagine not one, but 3 or 4 particles linked by entanglement across space and time. An experimenter, let's call her Alice, measures her particle. Then a second experimenter, Bob, far away, makes a choice about his measurement. Finally, a third experimenter, Charlie, even farther away, performs an action that could theoretically influence Bob's earlier choice. By analyzing the intricate web of correlations between all the particles, physicists hope to find a pattern, a unique signature of influence that could not be explained by many worlds, or by signals traveling forward from Alice, or even by simple spooky action at a distance. They are looking for a 3-way correlation that has a temporal twist, a signature that can only be produced if Charlie's future action is part of the explanation for the results Alice gets in her past. These experiments are not yet fully realized. They exist on the borderland between theoretical proposal and technological feasibility. They require a level of control over quantum systems that is at the very edge of our current capabilities, demanding the creation and manipulation of fragile, multi-particle, entangled states that can vanish with the slightest disturbance. The theoretical work is equally intense. Physicists like Ken Wharton and Hal Price are not just proposing experiments, they are trying to build a new mathematical foundation for physics, one where the laws themselves are time-symmetric. They are constructing models where the state of a system at any given moment is determined not just by its past, but by a combination of its past times and times its future boundary conditions. In this view, the universe is not a story being written from beginning to end. It is more like a solved crossword puzzle. The answer to one across is constrained not only by the clue, but also by the letters required for 2 down and 3 down. The past and future constrain each other, co-creating the present moment in a seamless, self-consistent whole. These theories are profoundly radical. They suggest that the arrow of time, our intuitive sense that time flows inexorably forward, might be an emergent property, a statistical illusion born from the thermodynamics of large, complex systems like ourselves. For a single isolated quantum particle, time may not have a preferred direction at all. It may be a 2-way street. For now, the laboratory results remain tantalizingly ambiguous. Some experiments, like those led by pioneering physicist Ephraim Steinberg, have produced results that are disconcertingly consistent with the retrocausal picture, pushing the boundaries of what can be explained by classical intuition. Yet none have delivered the final unambiguous smoking gun. No signal has been found that definitively slams the door on all other interpretations. The scientific world holds its breath, caught in a state of profound suspense. The community is a microcosm of the quantum state itself, a superposition of belief and skepticism. Many physicists remain deeply unconvinced, viewing the pursuit as a fascinating but ultimately peripheral endeavor, a philosophical indulgence rather than mainstream science. They argue that focusing on interpretations is a distraction from the more practical work of using quantum mechanics to build new technologies like quantum computers and sensors. For them, the theory works perfectly well as a predictive tool, and questioning its fundamental causal structure is unnecessary. But for the researchers on the front lines of this quest, it is anything but a distraction. It is the most fundamental question we can ask. They are driven by the conviction that understanding why quantum mechanics works the way it does is paramount. They believe that buried within this paradox of causality is a key, a clue that could unlock the next great revolution in physics, perhaps even uniting the seemingly incompatible worlds of quantum mechanics and Einstein's theory of general relativity. Their work is a testament to the unyielding spirit of human curiosity. It is a declaration that we will not be satisfied with a set of rules that merely predict reality. We want to understand the story reality is telling. They continue to refine their methods, build quieter labs, design more clever causal traps, and sift through mountains of data searching for that one subtle, anomalous signal. Each new experiment is a roll of the dice, a gamble for the highest stakes imaginable, our understanding of time itself. Every null result only deepens the mystery, reinforcing the confounding perfection of quantum mechanics as it is. Yet every tantalizing flicker in the data, every statistical anomaly that defies easy explanation, fuels the fire of their search, whispering a promise that they are on the right path. The final verdict is not yet in. The court of science is still in session, and the evidence is being meticulously examined. We stand at a precipice, peering into an abyss of possibility. For decades we have used quantum theory, but we have never truly understood the reality it describes. We have been like sailors navigating by the stars, trusting their patterns without understanding the gravitational dance that dictates their motion. Now we are building the telescopes to finally see that dance up close. But what if they succeed? What happens to us, to our perception of ourselves and our place in the cosmos on the day the noise is silenced and the signal comes through clear and undeniable? What becomes of our world when we learn with the certainty of science that the future is not an undiscovered country we are sailing towards, but a silent, unseen partner in the very creation of the present? And so we stand at the precipice, looking back from the summit of an intellectual odyssey that has taken us from the solid ground of classical reason to the shimmering, vertiginous edge of reality itself. The ground, it seems, has vanished from beneath our feet, replaced not by an empty void, but by a seething, paradoxical ocean of quantum potential. We began our journey seeking answers, armed with the simple, elegant logic of cause and effect, a principle that has served as the bedrock of science and sanity for millennia. We drop a stone, and it creates a ripple, a star collapses, and a black hole is born. The arrow of time, we were certain, flew in one direction only, from a fixed past towards an open future. This was our map, our compass, our most trusted guide through the labyrinth of the cosmos. But the universe we have discovered does not feel obligated to conform to the limits of our intuition. The map is not the territory. Down in the deepest foundations of existence, in the realm of the photon and the electron, we found not a simple chain of causation, but a conversation, a silent, instantaneous dialogue that appears to stretch across the fabric of space-time itself. We have been forced to confront a possibility so profound, so utterly subversive, that it challenges the very definition of before and after. The whispers of retrocausality, once confined to the most speculative fringes of physics, have grown into a persistent, undeniable chorus echoing from every experiment that probes the quantum mystery. Our journey has forced us to retrace the steps of giants, from Einstein's steadfast belief in a local deterministic reality to Bohr's insistence that we live in a participatory universe where the act of observation is an act of creation. We saw how Bell's theorem transformed this philosophical debate into a stark experimental question drawing a line in the sand. On one side lay the comfortable classical world of our senses, on the other, a reality of bewildering strangeness. Over and over again, the universe has shown us its choice. It has consistently, stubbornly, and unequivocally sided with the strange. We have followed the ghost of a single photon through the cosmic interferometer of Wheeler's delayed choice experiment, a thought experiment made real. There we witnessed what appears to be the impossible, a decision made in the present, seemingly reaching back in time to dictate the past behavior of a particle. It was here that the linear narrative of time began to unravel, not as a flaw in our instruments, but as a fundamental feature of the cosmos we inhabit. Was the photon a particle or a wave? Its history, its very nature, seemed to be held in a state of suspended animation, waiting for our future choice to collapse it into a single concrete reality. This idea that the future could cast a deciding vote on the events of the past is the central explosive revelation of our investigation. It's a concept that feels like a violation, a logical trespass. Yet the mathematics remains unblemished, the experimental results unambiguous. We have been compelled to entertain theories once considered heretical, like the transactional interpretation, which paints reality not as a sequence of events, but as a vast space-time negotiation, a handshake between an offer wave moving forward from the past and a confirmation wave moving backward from the future, with the present moment being merely the point where their agreement solidifies into the world we experience. Confronting this has required more than scientific rigor. It has demanded a kind of intellectual courage. It has forced us to dismantle the very scaffolding of our thought. For what is our mind if not an engine of cause and effect? We learn, we remember, we plan, all based on the unwavering assumption that the past is the immutable foundation upon which the present is built and from which the future unfolds. To even consider that this flow might be a two-way street is to risk a kind of intellectual vertigo. It challenges not only our physics, but our philosophy, our psychology, and our most intimate sense of self. The river of time, a metaphor as old as language, may be a profound illusion. Perhaps time is not a river at all, but a vast crystalline block, the block universe of Einstein, where all moments exist simultaneously. And if so, then quantum mechanics has just revealed the secret pathways, the hidden veins of causality that run through this crystal in every direction. This is not a mere reordering of the cosmic furniture. This is a complete reimagining of the house. We are forced to ask, what does it mean to be in a universe where the past is not truly past? If a choice we make tomorrow could have, in some subtle but real way, influenced the quantum coin flips that occurred billions of years ago, then our perception of history is fundamentally incomplete. We see history as a finished book, its pages written in indelible ink, but the quantum realm suggests the ink may never truly dry. The story is not merely being read, it is being constantly, subtly, and non-locally co-authored by events throughout its entire span. Our role in the cosmos is transformed. We are not just passengers on a vessel sailing the currents of time. We are only just beginning to comprehend navigators who may be subtly influencing the very currents that carry us. We are at once the products of the past and it seems the architects of it. This revelation sends shockwaves far beyond the confines of quantum mechanics, crashing against the shores of our grandest scientific ambitions. For decades, the two great pillars of modern physics, general relativity and quantum mechanics, have stood in magnificent but stark isolation. One describes a smooth, deterministic, geometric universe of the large. The other, a chaotic, probabilistic, and bizarre universe of the small. The greatest challenge in all of science has been to unite them to find a single coherent theory of quantum gravity, but they have refused to reconcile, speaking fundamentally different languages about the nature of space, time, and information. General relativity's block universe is static, a pre-written history. Quantum mechanics, with its collapse of the wave function, seems to demand a dynamic, evolving present. Could retrocausality be the missing Rosetta Stone? Could this two-way flow of influence be the key to translating between these two disparate languages? If causality is not a simple forward-marching arrow, but a complex network of influences binding the block universe together, then perhaps the conflict was never a conflict at all, but a misunderstanding. A unified theory might reveal a cosmos where the large-scale geometry of space-time dictated by relativity is constantly being informed and sustained by quantum transactions that echo backward and forward through its history. The shape of the universe today might be a consequence not just of the Big Bang, but of all the quantum events that would ever happen within it. A grand, self-consistent causal loop writ large across 14 billion years. The universe in this view would not just be expanding, it would be becoming itself at all times simultaneously. This idea reaches its most staggering conclusion when we turn our gaze to the ultimate origin, the Big Bang itself. We have long struggled with the fine-tuning problem, the baffling fact that the fundamental constants of nature appear to be exquisitely improbably calibrated to allow for the existence of stars, planets, and life. Change the strength of gravity by a minuscule fraction, alter the charge of the electron ever so slightly, and the universe would be a sterile, empty void. We have explained this away with theories of a multiverse, an infinite lottery, where we simply happen to win the cosmic jackpot. But retrocausality offers a more elegant and perhaps more profound alternative. What if the universe is not finely tuned by chance but by necessity? Imagine that the existence of conscious observers like us, millions or billions of years in the future, is not just a random outcome. What if the act of our observation, our existence, our very consciousness, is the final term in a colossal cosmic equation? If the future can influence the past, then perhaps the conditions of the nascent universe were not random at all. Perhaps they were constrained, shepherded, and selected by the requirement that the universe would eventually produce beings capable of observing it. In this breathtaking vision, the cosmos is a kind of self-portrait painted from a future vantage point. We, the observers, are not an accidental afterthought. We are in a very real sense woven into the fabric of its creation. Our future existence could be the unseen anchor that stabilized the chaos of the beginning, the gravitational pull from tomorrow that helped shape yesterday. We would be, in the truest sense of the word, children of the cosmos, who helped write our own origin story. This brings us inevitably to the final and most personal frontier ourselves. What does a retrocausal world mean for the human experience? Our deepest anxieties and highest hopes are tied to the nature of time and choice. Does this new picture of reality rob us of our free will, locking us into a predetermined fate within a static block of space-time? Or does it paradoxically grant our choices a significance far greater than we ever imagined? The answer may be a beautiful, unsettling synthesis of both. Perhaps the future is in some sense already written, but it may be written in a quantum language of probabilities and potentials, not in the classical language of certainty. And perhaps our choices, our acts of conscious will, are the very mechanism by which that probabilistic future reaches back to collapse the past into the concrete reality that led to us. Our free will in this model would not be the freedom to change a settled past, but the power to select which of many possible pasts becomes the real one. Each decision you make, every path you choose, might not just be forging your future. It could be sending ripples backward, solidifying the quantum history that made your choice possible in the first place. You are a living, breathing nexus of cause and effect, a focal point where the threads of yesterday and tomorrow are gathered and woven into the singular tapestry of now. This is a responsibility and a power far beyond our everyday comprehension. It suggests a universe that is not a cold, indifferent machine, but a dynamic, interconnected organism, a cosmic nervous system where every part is in communication with every other part across all of space and all of time. We are left here at the end of our exploration, humbled and awestruck. The simple questions we started with, what is a cause, what is an effect, have blossomed into the most profound mysteries we can contemplate. We have peered into the quantum heart of reality and found a reflection of ourselves inextricably linked to the first moments of creation and the last moments of time. The solid certainties of our ancestors have dissolved, but in their place we have not found chaos. We have found a deeper, stranger, and more magnificent order, an order where the past is not a memory, the future is not a dream, and the present is the extraordinary junction where they meet. The universe is not a story being told to us, it is a story we are telling, with it a story whose beginning is influenced by its end, and whose end is shaped by its beginning. And as we continue to gaze into its depths, we must accept that in this cosmos, The conversation between tomorrow and yesterday is always happening silently, in every atom, in every star, and within each and every one of us. The journey is far from over. In truth, it has just begun.